We're going to investigate the spherical square well today, or spherical infinite well today. And our goal is to make those probability density plots of the variety you see in Griffiths, at least for the hydrogen wave functions, but we just want to get the idea for the spherical infinite well as well. So my goal for what I want at the end is a figure window. Well, actually, we're going to make like 3 figure windows pop up. And each figure window is going to have several plots in it. I don't know if you guys have used subplots before, but we'll talk about those. So it's going to be a 3 by 3 grid. There will actually only be 6 plots in there. And the idea is I'm going to, well, so this is like X and this is Y here, or you can think of R equals 0 is at the center and theta is increasing as we go down, right? If we're thinking in spherical coordinates. And we want to plot those probability density plots for the cases L equals 0, L equals 1, L equals 2. And of course, when L equals 0, the only allowed M is 0. When L equals 1, M could be -1, 0, or +1, but the -1 and the +1 are actually going to have the same probability density as a function of R and theta. The only thing that changes is whether you have an e to the im phi or e to the minus im phi, but if we just plot the magnitude of psi squared, we're going to see the same thing. So I only need to consider the non-negative m's. So this will be L equals 1, M equals 1 there, and of course, M equals 2 would be allowed for L equals 2, as well as M equals 1 and M equals 0. So our goal is to make those probability density plots where, you know, something is getting brighter or dimmer, you know, and we might have something that, you know, kind of has a blob there and a blob there and a blob there and a blob there, but it's getting continuously brighter or dimmer as a function of position. We'll just have to see what they look like, right? And well, we're going to produce different figures, one that has no zeros at any finite radius except possibly R equals 0, one that has 1 0 on the way out to infinity, and then maybe a third plot that has 2 zeros going out to infinity for all of these cases. Now, let's just back way up and talk about how to plot things like this, which you've probably done before, you know, at least if Dr. Rodenborn's still doing the same kind of stuff in Physics 230, but it's easy to forget. Last time, or for our other assignment, we were using the plot function, right? We would say, oh, I've got a vector X, and I've got something that's the same size as X that carries the values of psi at each X, right? And we were just going to plot them, and it gives a nice plot like that in 1 dimension. What if I've got a function of 2 dimensions? In other words, I want to draw the xz plane, or things as a function of theta and r. So I want to draw something in a plane. Well, you know, in this case, when we plot psi as a function of x, we're plotting the height of psi as a function of x. And the analogous thing for a function of 2 dimensions would be to show a surface above the xy plane. The bad thing about surfaces is that they're really hard to read numbers off of, right? If you want to say, I want to know exactly at x equals 2 and y equals 3, what's the height of the function? You get this perspective view of a bunch of hills and valleys, and you can't really see the numbers, right? So that's not so great if you want to analyze the plot very carefully. The other option is to actually just make a 2-dimensional plot. In other words, make x go along here and y go along there. And instead of showing the height of the function as a function of those, where we need a perspective kind of plot, we could just show some colors, and the color indicates the height of the function or the value of the function. And we would have a color map that shows, you know, how things change. So the corresponding command, and we'll talk about how to use it. Hopefully you've seen this before. Image SC for a scaled image shows, you know, maybe I have 100 X's and 100 Y's. And so this would be a 100 by 100 grid of little colored points. And the color is going to change as a function of position. Jake? I know I'm not going to worry about it too much because I keep resetting it. And then when I walk forward, we really need to have there's a Logitech control thing, and it's at least not on my laptop here. And it allows you to turn off the autofocus so that if you want to just focus on a fixed plane, we'll see if it stays, but it keeps focusing on me and then not being able to adjust. But thank you. So that's how we're going to plot this, with sort of a color map like that. And let's just start building up something in MATLAB that's going to allow us to do that, play around with it. And well, I guess maybe it's worth saying a couple more things about this. What am I going to plot with this function? Well, it's got to be a function of two, it's got to have two indices on it, right? One index that varies with X and one index that varies with Y. You know, so here I just had, you know, when I was forming this vector X, you know, I might say X is equal to linspace. You know, maybe I want to start, you know, at some X min value that I've defined, go to an X max, and then do the number of X values that I want. And so the question is, what is the corresponding, something that corresponds to a linspace function, but will create for me two-dimensional variables that I can write, right? And, you know, let's suppose I want to plot the function, my function of X and Y that I want to plot, this is just completely made up, is X times Y squared. Right? That has a different height at every X and Y, right? When X is equal to 0, it's certainly 0. When Y is equal to 0, it's 0, but it has different heights at different locations. How am I going to do that? You know, the same way, you know, here, if I wanted to plot the function X squared there, what I would do is just take the dot square of X, square every element of it. So what's the corresponding thing we're going to do here? Well, something that's similar to linspace but creates two-dimensional arrays of variables is called mesh grid. I don't know if you guys have used that before. Maybe Dr. Rodenborn introduced it to you. So what I would do to start out with mesh grid is I define, just the same way I would in one dimension, what my vector of X values is going to be and what my vector of Y values is going to be. And so I might say, well, let me just do it in MATLAB. Sure, show my screen up here. So I'm going to define the number of X points I'll have, number of Y points, and I'm going to use a linspace to define the vector of X values. And I, you know, just so I could make sure that I knew when I see these two-dimensional plots to make sure my X is along the horizontal and Y is along the vertical, at least to start out with, I'm going to make X have a different, X is going to go from -3 to 3 and Y is going to go from -2 to 2. And that way I'll just be able to make sure, even though, so I'll be able to see the one that goes from -2 to 2 is supposed to correspond to Y, in case I'm ever unsure. We can change it back so that they're equal ranges to begin with. So how am I going to create the variables to build up those functions of two dimensions? And so the command that's sort of like linspace, but for two-dimensional functions, is called mesh grid. And the way it works like this is, we're going to create an array that's called capital X, usually, conventionally, and another array called capital Y. And those are going to be the outputs of the function. And they're going to be functions of little x and little y. So we do mesh grid of those two functions right there. And what that does when I execute it is create a two-dimensional grid X and a two-dimensional grid Y, where the one labeled as X only varies along the X direction, but it's constant along the Y direction. And the one that's labeled Y, it only varies along the Y direction, but is constant along the X direction. And maybe it's worth visualizing these to begin with, just so that we get an idea of what it looks like. So let me create a figure window. I'm just going to open up figure window 1 and show you how to plot one of these color plots that probably most of you have seen before. The command is image SC, that's a scaled image. You first give the vector that you want along the horizontal, then the vector that you want along the vertical, so my X vector and my Y vector. And then the thing I want to plot as a function of those two variables is this X. So I'm going to visualize what the output of MeshGrid is. Let's just visualize what the X array is. It's something that varies as a function of X. So let me run this. And here's a picture. Remember, my X is going from -3 to 3. So the horizontal direction definitely is X. My Y is going from -2 to 2. And that's definitely Y there. And notice this array X, which I'm showing in color right here, only varies with the X direction. In other words, it's what the function X would look like as a function of X and Y, right? If you say my function f of X, Y is just X, it doesn't change as you move along Y. It only changes as you move along X. Now there's some problems with the plot that I have so far, and maybe it's a good time to fix these. One is I'm viewing a region, well, I guess the most egregious of them is the fact that MATLAB displays two-dimensional images like we display matrices, and the row index always increases as you go down. And so it's displaying this plot with negative numbers up at the top and positive numbers down at the bottom because, you know, the row index increases going down when we usually display matrices, and MATLAB is sort of built around matrices. So there's a way to fix that using the axis command. Axis XY should flip it up and down. So that means I want my Y coordinate to go upwards. So let me just run that again. Did that work? Something went wrong there. I thought I clicked run and it didn't run. No, maybe I didn't actually hit the run button. Try it again. There we go. So my axis XY command has started now the Y going from negative to positive along the vertical. That's good. So my second complaint is that 1 unit on the horizontal axis is a different size than 1 unit on the vertical axis, right? This distance in my plot is smaller than this distance here. And usually when we're viewing a region of the XY plane, we'd like to view it so that the X spacing and the Y spacing is the same. That's also an axis command. I can use it on the same line, and that is axis equal. So I can add an equal after a space there. That will, so I'm going to reverse the Y direction coordinates and make them equal. And when I do that, notice now that 1 unit distance on the horizontal axis is exactly the same as 1 unit axis on the vertical direction. So it's not distorted at all. That had an unfortunate consequence of putting these white bars on the top and the bottom. Anybody know how to get rid of the white bars? MATLAB experts? In other words, I want the axes to be trimmed down so they don't display this extra white space there and there. I could do that. There's an easy way to do it without thinking so much, and you know, you may want to adjust the bounds later on, so that's a good idea. But if you just do axis tight, that means only display the region within the axes that contains the data of, you know, that is being displayed. So only use as much axis range as you need. So now again, if I run it here, it's the same as before, but it's cropped out that little bit of extra white space, and that just makes it look nice. And of course I could use X label and Y label to label the X and Y direction. So that's a graph of the array X. It only varies along X, and of course the array Y, if I displayed it using the scaled image, it only Whoops. I'm not hitting that button there. It only varies along the y direction, but is constant along the x direction. So those are our basic variables out of which we're going to build something. And if I wanted to plot the function, say, xy squared, which we normally write the way I'm showing on the board there, if I wanted to plot that, all I do is form that function out of these arrays, and I have to use dot times and dot square. And what that means is at every point in this two-dimensional array space, take the current value of x times that local value of y squared everywhere. And when that allows me to form functions of two or more variables. So here's what a plot of x times y squared looks like. And does it make sense? Well, certainly in the center, well, I guess I can't see what the values are. So there's one more thing I'd like to see on here, and that's what the color scale is. And I can do that by executing the color bar command. Color bar command puts a little color bar up here that tells you what the colors mean in terms of the height of the function. That's useful too. So 0 on my color scale is sort of a, mostly greenish, but a little bit greenish bluish color. So this is 0 here. Notice that my function seems to be 0 everywhere at x equals 0, and it's 0 everywhere at y equals 0. And at least that makes sense, right? Because x times y squared is going to be 0 when either x is 0 or y equals 0. And it's going to get bigger as you get farther away from the origin in other directions. So that seems to make sense as a function. Any questions about mesh grid or image SC? Just as a generically useful thing. Now, I'm showing you how to plot a function in Cartesian variables. We want to plot functions in polar coordinates because that's how they're specified in the function. We had those spherical Bessel functions and associated Legendre functions. We're going to be using those. They were functions of spherical coordinates. So instead of plotting things as a function of x and y, I want to define a function that I'm going to call r. And a lot of times in MATLAB, when people it's a good convention to stick by that when you use a capital variable, it usually means it's a function of more than one dimension. So x is going to be an array that represents a region of space. So what? I'm going to define the function r. R is a function of x and y. And in fact, the way it's defined in terms of x and y is the square root of x squared plus y squared. So let's define that spherical coordinate r, which at least in the xy plane is just the square root of x dot squared plus y dot squared. And we're going to use that. And now when I do my image SC, I'm just going to plot r and make sure it looks like it's working. So instead of plotting x times y squared, I'm just going to plot an image of r and run it. And there's my graph of r as a function of x and y. It looks like it makes sense, right? 0 is the deep blue color. That's right at the origin. And then it's getting higher and higher values as you go further and further away from r. So that seems like it's working. I've got a plot of r as a function of x and y, right? I'm also, of course, going to want, maybe I'll pause for a second because people are looking and typing. I'm going to want the variable theta. So I'm going to think of, maybe I've got my labeling wrong here. Maybe I should call what I'm calling y. We usually think of that as the z coordinate, right? So I'm going to do a little change of labeling here. I'm going to label what I was calling y z, and I'll keep x the same. So it's like we're looking at things in the xz plane. So z is going to be up in my diagram. And then in my mesh grid, I'm just going to call my y now capital Z. Maybe I'll change my ny to an nz. I didn't realize that I hadn't changed that before, but maybe it will make more sense. So we're looking in the xz plane now, changing all my y's to z's. And so I've got a variable r that as a function of this plane has the values of the radial coordinate. Now I also want something that tells me at every point in the plane, what is the corresponding value of theta, right? Relative to the origin, what theta am I at, where theta equals 0 is up, usual way. So let's figure it out. Here I am in the xz plane, and here I am at an arbitrary point which has coordinates x and z up there, right? And this is the angle that we would normally in spherical coordinates call theta. And well, let's see, this distance is x, this distance is z, so it seems like the tangent of theta is going to be equal to opposite over adjacent, right? Tangent theta is x over z. And, you know, that's certainly going to work as long as I'm in the first quadrant. There is, well, certainly tangent of theta is defined that. So I would like to say that theta is equal to the inverse tangent or arctangent of x over z. Instead of using the inverse tangent, there's something in MATLAB called a 4-quadrant inverse tangent. You know, the inverse tangent always has those problems as you have to worry about what quadrant you're in to see whether it works right. If you want a function that works in any quadrant, there's a function atan2, which instead of just taking one argument, x over z, it separately takes the arguments x and z. And I'm going to use my capital X and my capital Z, and it's going to calculate as a function of those what the inverse tangent is. And we're going to plot it and check that it looks like it's doing the right thing. Now, the only problem with this is, of course, the tangent of theta switches signs when theta goes from positive to negative, right? And so I'm going to actually have this is going to be labeled as a positive angle, whereas over here, this is going to be labeled as a negative angle if I use this function. So I probably also, in order to get the correct as a function of the xz plane, these should be positive angles. These should also be positive angles over here. That's the way we usually label it. Let's just take the absolute value of it. That's my guess for what theta is. Maybe I'll just call it capital theta because it's a function of position in the plane. Let's go back and see if that works. So I've got my r defined. I'm going to leave r there and let me define theta. Oops. Is equal to atan2 of, what did I say? X over z. So I put separately x and then z in there. And then I'm going to take the absolute value of that. Okay, putting in my semicolons as it warns me about. And then let me image see what theta is and make sure I didn't make any mistakes there. Say that again. Oh, I still have y. Oh, yes, yes. So this would be my z, yeah. All right. So does that look good? Theta, so 0 is the deep blue. So here's theta equals 0 there. Notice theta doesn't change along the radial direction. The colors are constant if you head away from the origin, but it's going from 0 up here to a number that's a little bit bigger than 3, that's pi, down there. And it's the same on both sides. So that seems like a sensible definition of what that angle theta is, going from 0 to pi on both sides of the z-axis for my plots. Okay, so I've got my basic variables. I've got r, I've got theta. Now I can write down functions of r and theta, right? I could say, maybe I want to visualize what r squared times theta is. I would do r dot squared dot times theta, and that would give me a plot of r squared times theta. There it is, right? We should think about whether that makes sense. When theta equals 0, certainly this should be 0. As r gets bigger, the value of the function should get bigger, and it seems like it's doing generically the right thing. So I can make functions of r and theta, and of course we're going to be using those spherical Bessel functions and associated Legendre functions in what we're doing. Let me just make sure there's nothing else I wanted to say on this before we go to those. I don't think so. So let's go back and look at our slides from, in fact, our slides, I've put together a bunch of pieces, just reminding us of the pieces for the infinite square well, right? We have a function as a function of r that eventually goes to 0, and it stays at 0 forevermore. So we got to keep that in the back of our head. But inside the region where it's non-zero, right, inside that spherical square well, the radial part, remember, it was a product function. These are the kinds of functions where we separated variables, and we're finding product functions, a function of r times a function of theta times a function of phi, and we're not going to worry about the phi part. We're only concerned about the product of the function of r times the function of theta. The function of r is called a spherical Bessel function, and it oscillates along the radial direction with its amplitude getting smaller and smaller. The symbol is in Griffiths is JL of KR. And so the argument of this spherical Bessel function is KR. And let's now see how to do that in well, actually, it looks like I decided here that I actually want to do the angular part first. Okay, so that's what's going to happen along the radial direction. The full wave function, of course, is equal to 0 if r is greater than a, or it's a product of that spherical Bessel function times the spherical harmonic as a function of theta and phi. And the spherical harmonic is a product of e to the im phi, which we're going to ignore because we're going to be plotting the magnitude of psi squared, times this associated Legendre function, where the associated Legendre functions have their polynomials in cosine of theta or sine of theta. Okay. So the first thing I want to talk about is we've got the variable theta. How do I get the associated Legendre functions as a function of theta? Let's go back to MATLAB now. Yeah, and you got to, this is where you Google something and look up how to do it. And so I'm going to, of course, these associated Legendre functions are functions of, they depend on both L and M. L is the lower subscript, M is the upper subscript. So I've got to know what L and M are. For this point in my code, let me just define what L and M are. So I've got my theta defined. Let me say L equals 2, for example, and M equals 1 just to test things out. And we're going to try to get a picture of what P21 looks like as a function of theta. And of course, it shouldn't be a function of r. It should be constant as a function of r, but it should vary with theta. And then we'll compare to the picture that I just showed you, or the table of functions, and see if it makes sense. The associated Legendre functions are given by the function Legendre in there. So I'm going to say, let me define my Legendre functions. I just called them P because in Griffiths, they're defined by the symbol P, right? And they're functions of L and M, and they work in a little bit of a strange way. So I'm going to set it equal to, the function is Legendre, okay? And it takes some arguments. The first argument is the L value. So I'm just going to put my L in there. The second argument is the thing that it's a function of. And so it's going to be a function of cosine of theta, where theta is my two-dimensional variable. So the second argument is going to be cosine of theta. I'm using my capital T theta, which is that function of x and y. And what that gives me is going to be something that's not only, of course, I've told it what L is. I didn't tell it what M is. And what it does is it spits out all the possible M's. So when I execute this function, it's going to give me an output. Let's see, I chose L equals 2. So my possible M values are M equals 0, M equals 1, M equals 2, because the M equals -1 and -2 are actually the same as the +1 and +2 for these. So we only need the non-negative M values. There's going to be 3 different M's. So it's going to give me an array that is 3 by however many X values I have, by however many Z values I have. So it's going to give me a 3-dimensional array, right? The first one's just going to have 3 elements. The first row in there will be M equals 0. The second one will be M equals 1. And the third one will be M equals 2, because I chose L equals 2, and there should be 3 different values of M. So if I wanted to plot that, for example, for L equals 2, M equals 1, maybe it's better to call this P2 because it corresponds to L equals 2. And let me just get an array, which is, I'm just going to call it P21. That would be L equals 2, M equals 1. How am I going to compute that with this? Well, I'm going to take P2, which all corresponds to L equals 2, because I already told it what L is. And if I want M equals 1, well, let's see, M equals 0 is the first row. So I want the second row. In other words, whatever my M value is, I have to add 1. Oops. You could just put a 2 in here, but I'm gonna put M plus 1 because it'll work for any M value. And then I want to just keep all of the second and third array indices, because those tell what it's doing as a function of X and Y. Sorry, as a function of X and Z. So if I take the second row, right, M equals 1, so this will be 2. If I take the second row and then all the second and third indices, it's going to give me something that's a function of X and Z in those indices. And we'll see that there's a problem, but let me just try to plot that, and we'll see we get an error. Let me plot P21. I've defined that function P21. It should give me an error. Yes, so it died, and it's saying the problem is I had something that was, let's suppose my NX is 100 and Z, the number of Z points is 100. My P corresponding to L equals 2 had a size 3 by 100 by 100. And then when I calculated P21, that corresponded to M equals 1, I took the second row of this one, which then gives me something that's of the size 1 by 100 by 100. Now, ImageSC is expecting something that's just a 2-dimensional array. Now, this really is a 2-dimensional array because, if you put a 1 by something, it's like nothing's happening along that dimension. It only has one element along that dimension. So this really is like it, but there's a way to sort of get around it, and that's with what's called the squeeze function. The squeeze function says anywhere you have a dimension that's size 1, you just sort of eliminate it from it. And that's what we need to do to make ImageSC happy. So I'm going to go back to my stuff I'm editing here. And instead of plotting P2, I'm going to plot squeeze of P2. That just means get rid of all the dimensions that are size 1 because you don't really need them, right? I could say the number 4 is a 1 by 1 by 1 by 1 array. Well, it's still just a number, right? I mean, there's no reason to keep all those 1s in there. So when I do that, hopefully my error goes away. And I get something that again, it's a function of theta only, so it's not a function of r. That seems to make sense. Let me go back to my slides here. And let's see, we did L equals 2, M equals 1. So if I look in the table here for P2, 1, that's this one in the lower left-hand corner. It should be sine of theta times cosine of theta. So it should have a 0 at theta equals 0, theta equals pi over 2, and theta equals pi. And, you know, it's going to start out positive, and then it will go negative later for beyond pi over 2. Let me just make sure that makes sense. So it has a 0. 0 again is this sort of almost blue-green color. So it has a 0 at theta equals 0, at theta equals pi over 2, theta equals pi. It's negative. Well, let's see. Does that make sense? It's negative sine of theta, cosine of theta. I've got something that's going positive here, but should my function be negative there? Looks like it has the right absolute value, but its sign is wrong, which I guess is okay because we're going to take, you know, that's sort of like a normalization constant for us. At least it's proportional to the right kind of behavior. I think if I'm reading this correctly, if it really were just sine of theta times cosine of theta, when theta is between 0 and pi over 2, both of those functions are positive. So it should be positive up here. And I'm actually seeing that it's negative, and then it goes to positive. But it seems to have the right behavior, at least in absolute value. I'm not sure if there's a normalization constant that I haven't figured out in here. But it looks like it's working in terms of absolute values, how it's changing as a function of theta. Remember, we're going to take the absolute squared of this whole thing anyway, so I don't really care about normalization constants, and certainly a factor of -1 is part of a normalization constant. Okay, that's good. So I've got my angular dependence, right? And I could change the different L's and M's and calculate, you know, each corresponding one. Maybe we should try another one. Let's try L equals 2, M equals 2, and see how that, if that corresponds. So this one is 0, then it goes to a maximum, and then back to 0. And if I go to my slides, P22, that's sine squared of theta, right? So that would start at 0, go to a maximum at pi over 2, and then go back to 0. And that one seems to be doing the right thing with the correct sign there. But okay, so I've got my theta dependence there. Now I want to figure out the radial dependence. So that's going to give us the function of theta dependence. Now, how do I get the radial dependence? The radial dependence were called the spherical Bessel functions. They have the symbol J. And MATLAB doesn't directly have the spherical Bessel functions in there. What it has is called the ordinary Bessel functions, but it's actually really easy to compute the spherical Bessel functions from the ordinary Bessel functions. And the ordinary Bessel functions are just given by the function Bessel. Let me just, so I'm going to just comment this out. So I've got it sitting here, and I'm going to start a new plot function down here. What do I want to call this? What did I call it in my notes here? I called it the Bessel function corresponding to L equals 2, and it's going to be a function of r and theta, but of course it should only be varying as a function of r. It's going to be a function of our variable capital R. Okay, and to calculate it, I'm going to use an ordinary Bessel function, which just has the function named Bessel. No capitalization. Oh, I'm sorry, not Bessel, but Bessel J. That's an ordinary Bessel function. To make it into a spherical Bessel function, what you have to do is, for the first argument, you have to take L and add 1/2 onto it. So, you know, the ordinary Bessel functions just have a different way of indexing things here. So if we want the spherical Bessel functions, you just have to add 1/2 onto L. I've erased what my L and M are, but let me just copy those down here. Copy, paste, uncomment. Okay. That's the first argument. And then the second argument should be whatever the argument of the spherical Bessel function is. And again, going back to my slides here, it's going to be a function of k times r, where k is related to the energy that we're talking about, right? And we're going to adjust k so that it goes to 0 right at k equals a. That's what we got to do to meet that boundary condition. But for right now, let's just define what k is. I'm going to say k is 2.5, for example. Let me just define that variable. We'll be varying k later on, but let's just take, I'm going to define something. K is equal to 2.5. And let's, so the second argument in Bessel J is just going to be k times my function r, capital R, which is a function of r and theta, which is that radial coordinate. So it's a Bessel function as a function of kr corresponding to my L value. So I've chosen, again, L equals 2 just as an example. Okay, so I've got that for my spherical Bessel function. And let's plot that spherical Bessel function using my image SC stuff again. Copy, paste, uncomment. I don't need a squeeze here. I'm just going to plot x, z, b2. And here's what I get. You should also know, you can change what colors correspond to what heights. Those are called different color maps. The default in MATLAB is something called Parula that goes from deep blue up to, for small numbers, up to bright yellow for large numbers. Okay, so again, so I've got something that looks like it's 0 right in the center, right? And then it's getting large. It looks like, well, let's see. 0 is, on my color map, I've got to kind of use my eyes. 0 is the color it has at the very center there. So it looks like it reaches that color again out here, and then it starts becoming negative. And that's that oscillatory behavior, right? We said the spherical Bessel functions keep oscillating up and down, but their amplitude gets smaller and smaller. Let's, just to look at the shape, we're looking at L equals 2. That's this dot dash curve it looks like here. It's hard to tell, but when k r equals about 6, it should have a 0. Let's just check that. My k is 2.5. So r is 6 over 2.5. So, a little bit smaller than 3, it should have a 0. Yeah, that seems to be at the right place where it has the 0. So this is the behavior as a function of r for the r part. Okay, so I've created the r part, I've created the theta part. Now I can multiply those things to get functions of both r and theta. And that's what we want to do in this case. Now, the problem is I still need to somehow get this r behavior. I really don't want it to actually keep oscillating all the way out to infinity. At some a value, I need to choose the radius of my spherical well. We call it a in Griffiths or in class. And I want to define an a value. Here I'm displaying things out at least to plus or minus 2. Let me define 2 to be the place where it goes to 0. Okay. I've just chosen a random k. Probably it's not going to be continuous. If I force it to be 0 after a equals 2, then we're going to see this just a sharp cutoff and it'll go to 0. Let's talk about how to put those zeros in there. So let me go back to MATLAB now. And maybe, I'm not sure what to call my radial wave function, but I'm building up the radial part of the wave function. I've already used capital R, so I'm going to name something RAD for the radial part of the wave function. And I'm going to start out setting it to be filled with zeros. And then I'm going to tell it to put in only the Bessel stuff where I want it to be. Okay, so let's fill it up with zeros, and I want my zeros to be the same size as, say, the array R. So zeros, parentheses, size R will give me an array that's the same size as R, which is the same size as X and Z too, but it's filled with zeros. And how can I then change the, and I haven't specified what A is. So let me define an A up here. In my examples I was doing by myself earlier, I chose A equals 2. So we'll be able to see that on our diagram. So I'm going to define A. That's going to be where it goes to 0. That's the edge of my spherical well. We're going to define, now I'm going to change what the values of the radial wave function are, but I only want to change it in the locations where R is less than A. So here's something that, you know, it's a little bit of an advanced MATLAB kind of way of doing things. But when I say, okay, my radial wave function is just filled with zeros to begin with. Now I'm going to assign something in only the indices that correspond to locations where R is less than the value A. That's going to be near the origin, up to R equals 2, right? I'm going to, and the rest of them where R is greater than or equal to A, I'm going to leave those as the zeros I've already set it to. So what I'm going to do is the Bessel function, but now since I'm only defining something where R is less than A, I've got to put a R less than A inside the argument of R. So I'm going to say, which R value should I use? Only the ones where the radius value is less than A. That's sort of saying, don't make this assignment for all indices, only the indices that correspond to the ones where the thing inside the parentheses is true. And now I don't want to plot B2 anymore. I'm calling it rad for the radial wave function. Let's just try that, see if it works. Tell me if I'm going too fast. Now look at what's happening here. It's very interesting. All of a sudden, my radial wave function just gets forced to 0, right? It's right at R equals 2 when it goes to 0. So I've got the kind of right behavior. I just haven't matched the boundary condition. It's not continuous. We haven't done anything to make it continuous. We're going to change that value K to force the 0 of the spherical Bessel function to happen right at R equals 2. But right now I'm just saying, hey, I've put a bunch of zeros in there, and then I set it equal to some randomly chosen spherical Bessel function inside there. But of course they don't match. It was at some finite value, and then it gets forced down to 0 after that. We're going to need to work to match that, just the same way that we had to work to find the energy eigenvalues in our one-dimensional problems that we were doing in MATLAB earlier. Okay, so that looks good right there. That's how I set part of an array equal to 0. Let's try, before we go and try to sort of develop what the final code is, let's try to put these pieces together. I've decided on an L and an M. Let's just leave K at the random value I chose for it right now. And let's try to multiply to get psi. Psi is going to be proportional to the function of theta that I got before times the function of R that I just defined right now. So here's my radial wave function. Let me pull the stuff that I kept up here for the Legendre function, and I'm going to leave the information corresponding to L equals 2, M equals, oh, let's go back to M equals 1. What the heck? Changed it just to look at another one. And let's copy that stuff down here before my radial stuff. I'm going to calculate the angular stuff. I guess I don't need my L and my M anymore. There, I've already got them defined. I'm going to set M equals 1 again, just to go back to the original case. So now I've got my P21 is my function of theta. and rad is my function of r. And if I multiply those two together, just like we did x dot times y squared, right? If I multiply my function of r times my function of theta, Bessel J was my function of r. So let me go down here below my rad function where I determined what rad was. Now I'm going to determine an array that's called psi, which is just going to be the product of the angular stuff times the radial stuff. Psi is going to be equal to rad dot times P21. I think that will work. And now let's get a little bit closer to plotting what we want to plot. I don't want to see psi, which has both positive and negative values. It's never imaginary because it's purely real stuff we put in there. But instead of plotting psi, I'm going to plot psi dot squared. Right? It's all real, so I don't have to worry about absolute values. So let's plot psi dot hat 2 and hope for the best. Doesn't look good because I'm not getting anything here. Some sort of error. Image SC. Oh, I forgot about my squeeze function, huh? I left out the squeeze. So instead of multiplying by P21, I better multiply by squeeze P21, right? This is how it goes with MATLAB. You know, you make mistakes, you look at the errors, and then you go, oh, okay, that's right. I forgot I left that thing out. Hey, that looks pretty good. You know, other than the fact that clearly I don't have things continuous at r equals a. I haven't bothered to worry about that because I chose a random k. We have to choose just the right k to make it go to 0 right at r equals a. So there's something artificial going on there. But I've got a function that is, again, for L equals 2 and M equals 1, we said there's a 0 at theta equals 0, at pi over 2 and pi. That looks good. And then the radial wave function we looked at, I believe there was some finite 0, but we're not even seeing it here because we haven't gotten out that far yet. So it's 0 at the center, and then it gets big, and then it gets smaller again. So that's going to be we're building up our picture of what the magnitude of psi squared is as a function of r and theta in the xz plane, for example. Questions so far? Am I going too fast, or is this okay? Everybody keeping up and feeling like they know what we're doing? So we're going to heavily leverage that piece of code. But now, really what I want to do is loop over some L's and loop over some M's, right? Maybe have a for loop. L equals 0 to 2, M equals 0 to 2. And I'm also going to have to loop over K's, right? I'm going to start with a very small value of K and make K bigger and bigger and bigger. Remember, K depends on the energy, and K are related. The bigger K is, the bigger the energy is. So as I make K bigger and bigger and bigger, that's taking all those wiggles in the radial wave function and making them sort of compress closer and closer to the origin. So at first, there's going to be the first 0 that lands at A, and that's what I'm interested in. And then as I make K bigger and bigger, that second 0 is going to come up and line just with A, and that's going to make it continuous again. And so let me try to put in a loop down here. Let's just leave L equals 2 and M equals 1 alone. We're just going to try to write a loop for K and get rid of that artificiality now, where all of a sudden it goes to 0. It should really be continuous at r equals a, and my a is 2 here, right? It's clearly not continuous. It's suddenly jumping down to 0. So I want to write a loop for K, letting K go from 0 to some maximum value. And every time I see the value, you know, my radial wave functions are going from positive to negative to positive to negative. So if I see the value of my radial wave function at r equals a go from positive to negative, that means I just passed a value where it's 0, right? So my goal is going to be the same kind of thing we did when we were looking for energy eigenvalues, where I always keep track of what the value of the radial wave function was at r equals a before, in the last time I went through. And then I'm going to take the product of the value of my radial wave function at r equals a and the previous time times the value it has this time. And if it's less than 1, I know it changed sign somewhere in there. So let's try to build up some code, but I'm going to need to do a loop over k's. So let's see, I need the r's and the thetas. I'm going to comment this stuff out, but let's build up a k vector. So I'm going to define, maybe I'll do 1,000 k's. So I'll say number of k's, num k equals 1,000. That's how many k values I'm going to test. And I'm going to make a k vector. I'll call that kvec using linspace. Let's make it go from 0 to 7 is sort of reasonable. I just found by experimenting before. And the number of values it has is num k. So that's going to be my vector of k values that I'm going to check. All k goes from 0 to 7. And then I've already defined what L and M are. Let me just redefine them down here because I'm going to comment this stuff out. So let's copy L and M down here at the bottom. Paste. And then let's do a for loop for k. For nk equals 1 to num k. So nk is going to keep increasing, and in each time in that loop, I'm going to set my k value equal to the k vector value with index nk. So it's first going to take the first k vector value, which will be 0, then the second one, then the third one, and each time we go through the loop, we're going to set the current value of k in there, and that's going then I can use my information like I had before. Okay, and now what I'm going to want to do is put it in if statement, and I'll fill in the details later. Let's put the end corresponding to that if down there. But the first time I go through this loop, I want to keep track of at r equals a, what the value, the sign of psi is at r equals a, and look for when it switches sign going to the next time through the loop. Okay, so at least when I was messing around with this, I made a variable called Bessel function, BESS at a. Looks like Bessata, but it's supposed to remind me of the Bessel function at a in this current time through the loop is equal to Bessel j. That's our Bessel function that we're using. The first index has to, or the first entry has to be L plus a half, L plus 0.5. And the second index is going to be k times a. Right? Remember, this is the argument. I'm just going to give it the single argument, whatever k we're on, times the value of a. And so that's going to tell me what that spherical Bessel function's value is at k times a. Now, if I chose k randomly, it's going to be either positive or negative. It's probably not going to be 0. But at some point through here, Bessel function at a is going to be positive and then it'll switch to negative, or it'll be negative and it switches to positive. And that's where I want to actually make the plot. Because when it just switches from negative to positive, it means it's going to be very close to continuous at a, because it's going to be going to 0 there, and then I'm going to hold it at 0 forevermore. Okay? So each time I go through, I'm going to keep track of that. And let me end my k loop. And then this if statement that I've left with nothing in it now is going to be, if something is true, I want to plot one of these ImageSC things, right? If the Bessel function at k times a has changed sign, and I'm going to say, let's multiply the old value times the current value and see if it's less than 0, right? If the old value times the current value is less than 0, that means it just switched sign and it's very close to 0. So if, again, same stuff here. I'm just going to copy the stuff I have for the Bessel J down there. If Bessel J, L plus 0.5, K times A times Bessel at A, that's the old value that I had from the previous time through the loop. If that is less than 0, that means it's just switched signs. And then what I'm going to do is do one of those ImageSC plots, but I don't want to go into this if statement the first time I go through the loop, right? Because I won't have defined what the old Bess at A is yet. So let me say and, that means just regular old anding these two functions together. And nk is greater than 1, right? Nk equals 1 would be the first time through the loop. I guess the first time through the loop, it won't know what Bess at A is. So I could just say Bess at A equals 0 before I go in there, just so it doesn't throw an error. But I'm never going to use that initial value because we're only going to go into this if statement if we're at least on the second time through the loop. If that's true, then I've just found a K value that makes the radial wave function go to 0 at R equals A. And then I want to do one of those ImageSC plots. So what I'm going to do is open up a figure window. And let's define what psi is. I've already got some good psi stuff up above, right? We said, here's how I'm going to define my radial wave function. So my radial wave function, I'm going to set with zeros and then fill it up with Bessel J's in the right locations. And then psi will be that times the appropriate Legendre polynomial, which we'll call P again. So let's copy that stuff down below. Indent appropriately. Okay, so if that's true, I'm going to compute what the radial wave function is. And then I've got to multiply it by the appropriate Legendre function. Okay, and I haven't defined what the Legendre function is here. But if I know L equals 2 and M equals 1, I can calculate that Legendre function exactly the same way I did before. And we'll have to make this work for other values too. But let me just paste that code up above. So I'm calculating the Legendre functions, all of them for L equals 2, and then specifying to M equals 1. And when I multiply those together, I'm still squeezing that function. Now I've got my psi, so I can use ImageSC and the axis stuff and the color bar, copying those down from the stuff we had above, indenting. And this is the point where it's like, well, I've changed so many things, I'm just going to hope that it works, but we'll see what happens. So I've defined what psi is. Psi is the radial wave function times the Legendre functions, those associated Legendre functions for the angular dependence, dot times together. I'm squaring psi. And I'll go back to this code in a second, but let me just see if mine runs here. Hey. That doesn't look so bad, except I was expecting, oh, I see. I've got a whole, it's opening up a bunch of figure windows. I see what's going on. This is figure 4. This is figure 3. I wrote my code so that it would just open up a new figure window every time it encounters this plotting routine. So let's just look at all these figure windows. Figure 1, did I not close that out? That doesn't look too good, does it? Figure 2 looks good. Do I not have a clear all, close all at the top? Oh, I see. I left my code in here. I need to comment this stuff above out. Let's comment that stuff I had above out and just leave in the stuff associated with this loop. let's close it all again. And it looks like it's plotting three different. What's going on here? Let's run it. Oh, I've got some sort of error here. Undefined variable A. Oh, I forgot. I commented out my A somewhere. So let me define, what did I say A was before? 2. That's a good value for it because that fits in our window. There we go. So each time it encounters this, it opens a new figure window. Now let's look at all these figure windows and see if we can make sense of them. There are 3 different figure windows. The first one is where that first non-zero value of 0 occurs at r equals a. So it's completely continuous. R equals 2, a equals 2. So it's continuous at 2, and then it stays at 0 forevermore. The second one is I keep making it k larger and larger, and that pushes those wiggles closer and closer into the origin. The second one has a 0 at some non-zero value, and then another one at r equals a. And then the third one has 2 wiggles, so 2 zeros at non-zero r values before it then again goes to 0 at r equals a. So that's actually what I'm expecting to see. We're making k larger and larger, and that's making the wavelength of those wiggles smaller and smaller. And we're looking for the points where those wiggles cross the axis just at the point r equals a, and then we throw up a plot. And these are the first 3 plots that I'm seeing there. Okay, so how are you guys doing? Are you guys following along with this? Good. So maybe let's see, what time is it? 10 o'clock. Maybe this is a good time to turn you loose. Now what I would do, we've got the basic algorithm here, but instead of doing just L equals 2 and M equals 1, I'm going to put a for loop for L and M, right, around this. So let me wrap my for loop for K with for L equals 0 to 2. Those are the ones we said we wanted to do in this plot. And then for M equals, well, let's see. I guess we only go from 0 to L for M, right? We don't need the negative ones because the plots won't be any different. So we're just going to go from 0 to whatever L is. I'm going to put N statements down at the bottom, and let's get the indentation right here. I've messed it up, so I'm going to indent the stuff in the middle. That looks good. And I guess the last thing we need to talk about is how to make these multi-plots in one figure window. So what I'm going to do is, I don't know if you guys have ever done this before. It's called subplot is the routine for doing it. So let me try to just alter my code to, instead of just opening up a random figure window, we're going to need to compute the appropriate Legendre function. Remember, when we calculate the Legendre function, you need to specify L first. So once I'm inside this L, copy. So let me copy this Legendre function thing. Once I'm in, I know what L is. I can calculate all of those functions, and I'm not sure what to call them. In my code, I call it P init, the initial P's that are associated with an L. But remember, when I call this Legendre function, it has all the M's in it. Once I figure out what M is, I have to pull out the appropriate row of that, right? So then when I'm in my M loop, I need to, now I can calculate exactly what P is as a function of R and theta, or as a function of X and Z. P is going to be equal to, well, let's see. There's a slight complication here, and that is, if you calculate the Legendre function corresponding to L equals 0, it's just going to be a 100 by 100 array. But if it's, Well, I guess this will work. So what I'm going to do is P is equal to P init. What row do I want to take? Well, if m equals 0, I want the first row. If m equals 1, I want the second row. So I'm going to do m plus 1 is the row, comma, colon, comma, colon. Right? We're going to take that element out of my initial P once I figure out what m is. The problem is when L, I guess there will be a problem here, and that is when L equals 0, there is no first element here. When you do Legendre with L equals 0, it doesn't give you a first array location because there's only one thing there. So we're going to have to do a special case here. If L equals 0, I'm just going to set P equals P init. Else, let's set P equal P init m plus first row and then all of the other array indices. And we're going to have to squeeze it so that ImageSC is happy with the result. Unfortunately, that's just, this is me sort of dealing with how MATLAB outputs these functions, right? So I'm saying when L is 0, there is no first index. It's just the 100 by 100 array. But when L is 1, there's a 2 by 100 by 100 array, and I've got to pick out the appropriate row of that one and then squeeze it so the one in the resulting thing isn't there anymore. Okay, that's just complications of doing that. Okay. So now I've got my Legendre functions. I'm calling them P. Is that consistent with what I have down here? Let's see. I'm calling it P21 down here. So let me just call it P. That's what I've defined it as now. P with and we don't need to squeeze it because I already squeezed it above. So it's just going to be R dot times P. Right. All right. So instead of ImageSC, let's see if we can, let me take out this figure right there. And let's figure out how am I going to get maybe 3 of these windows, one that corresponds to only that first 0 of the spherical Bessel function happening at A. The next figure window is going to be the one where the second one happens, and it's going to show as a function of L and M. So the first thing I'm going to do is before I do ImageSC, I've got to go into the appropriate subplot. So I don't know if you remember, it sounds like most of you are nodding your heads about having seen subplot before. The arguments of subplot is you first give the number of rows by the number of columns of plots you want. So we're going to do 3, 3. It's a 3 by 3 subplot. And then you've got to tell it which plot to activate, where the convention is, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I know the value of L, it looks like if I do, you tell me if this makes any sense to you. If I do 3 times L plus M plus 1. So let's imagine we're in the case L equals 0. It would just be M plus 1. So when M is 0, it's going to be the first one. When M is 1, it'll be the second one. When M is 2, it'll be the third one. When L is equal to 1, we're going to do 3. And then when M equals 0, that would be 3 plus 1 is 4. It'll give me this one. So I'm just creating a function here that goes 1, 2, 3, 4, 5, 6, 7, 8, 9 out of L and M. So this is going to be what subplot I want to use. Let me put that function in there and we'll see if it works. 3 times L plus M plus 1. That's the number of the subplot I want to activate. All right, and then we're going to draw this function inside there. And I guess The only thing I want to change in this code now is every time, so I want to fill this out for all the L's and the M's, but I would like to activate figure 1 when I'm at the first 0 of the Bessel function and so on. So let me see if I can figure out how to do this. Maybe we can say every time before I go into the K loop, I'm going to set some counter equal to 1. That's just going to be something that ticks up. And every time we pass one of the places where the Bessel function goes to 0 at r equals a, let's increase that counter by 1. Okay, so if I get in this if statement here that says, oh, we've got just the right k so that at r equals a, it goes to 0 there. Let's set counter equal to counter plus 1. So it's just something that's going to go up 1 time each time. And before I hit the subplot, what I'm going to do is figure counter. Okay, so let's think about this. The first time I get into this if statement, I've set counter equal to 1. So the first time I get into this if statement, I'm going to open figure 1 and do the plotting there. The next time, then counter will increase by 1. So the next time I get in here, I'm going to go to figure 2. And the next time I'm going to go to figure 3. But then when I switch to a different L and M value, counter is going to get set back at 1. So it's always going to tell me which one of these 3 images I'm going to be plotting in, right? The first time I do it, and if it goes up to figure 4, we'll see. I think I tested this before for this value of k max equals 7, and it worked. Always holding your breath as you hit run and see what happens. I can't hear, so it doesn't sound like much is happening. Some error for me. Incorrect use of the equals operator. Line 43. Oh, yes. Yeah, when you're comparing things to see if L is equal to 0, you have to use a double equal sign. That means compare L and 0 rather than assigning something. Okay, still doesn't look good. Looking at my errors, your errors may be different. Maybe you mistyped something. Line 39 refers to P2. Oh, this thing I don't actually need anymore. I just left it in there. So let's just eliminate my P21 or whatever it was. Hey, something's happening here. So I've now got some figure windows. Let's look at them and see if they make sense here. Not sure why these are so microscopic. Oh, I know. It's because I have a different X range and Y range. Remember, I set X to go from -3 to 3, and that's making these windows. I'm going to go X from -2 to 2, and to match the Z range that I have. And I think that'll make my subplots a little bit less microscopic. So it's plotting a bunch of stuff out. And I mean, I'll have to check the details. And what I want you guys to do is complete this, check the details. I probably also don't need the color bars in there. The color bars tell me exactly what the value means. But here, this is a probability density. It's not normalized anyways. So I'm going to probably take out my color bar stuff. That'll just make things less microscopic in the in the subplots. How that looks better. It's actually running much faster too. So this apparently, we got to check the functions. We can look in the book and sort of see. As a function, this is L equals 0, L equals 1, L equals 2, and this is M equals 0, M equals 1, M equals 2. And I've got to compare to those, and we can now see how things change. Notice I don't see any discontinuities that strike my eye at R equals A. In other words, at R equals 2. It stays at 0 forevermore after R equals 2, most of which I'm not displaying on here, but I'm just showing the interesting part of the function. It heads to 0, but it looks like it's continuous at R equals A. And I've got to look at my radial wave functions and see, well, okay, everywhere in my first figure window, which was supposed to be where the first 0 of that corresponding spherical Bessel function went to 0 at R equals A, there's a 0 at R equals 0, and then the only other one is as you head off to infinity. There's no zeros at finite R's, and that seems to be true of all these plots that I've thrown up in there. Whereas in the second figure window, there is a 0 at some finite A, and then it heads to 0 as you go to infinity. And in the third figure plot, there are 2 zeros at finite A's, but other than that, the stuff as a function of theta looks the same in these plots, which it really should, right? The theta dependence only depends on L and M. It doesn't depend on which K we've chosen to be the case.